Hello everyone. In this video, we will be tackling and simplifying the topic of amplitude modulation and frequency modulation of signals. Disclaimer: this video is intended for educational purposes as part of the public service video assignment for the course SKEE3533, that's Communication Principles, and presented by Group 11. First, what do we mean by modulation? To explain it, let's first look at the picture shown. We can notice that the two boys are very far from each other. If one of them talks in a quiet voice, it's nearly impossible for the other to hear him. Well, let's say we give that boy a speaker. Now the other boy can hear the voice clearly. In a similar manner, baseband signals, such as human voice, are often at low frequencies that cannot be efficiently transmitted directly through free space. Modulation is the process where we take this low frequency message signal and load it onto a high frequency carrier wave. In simple terms, we start with a carrier signal, which is a high frequency wave built to travel great distances and to be easily detected. Then we augment or change this carrier wave to match the exact pattern of the voice we want to transmit, often called the modulating signal. This final combined wave is what we call the modulated signal. Demodulation is the process where the receiver deciphers this augmentation and restores back the original message. So, let's tackle two of the ways we can do this augmentation, see the differences between them, look at the current advancements, and talk about some public concerns. First, amplitude modulation. Shown on the left is the high frequency carrier signal. On the right is the modulating signal, or the message if you like. Amplitude modulation is the process in which we augment the carrier signal's amplitude according to the modulating signal to produce this modulated signal. We can notice how the frequency of the cycles remains the same, but the amplitude is varying. A receiving system will later decipher this variation in amplitude to produce back the original modulating signal. Now, due to the fact that the Earth's atmosphere has a lot of static electricity, this static intervenes with the modulated signal in the form of noise. It causes random peaks in the amplitude of the signal, distorting the transmitted message. Because of this, a major disadvantage of amplitude modulation is its high susceptibility to noise. Moving to frequency modulation. This time, the waveform of the modulating signal is translated to variations in frequency on the carrier signal. As you can see, the amplitude remains the same, but the frequency changes accordingly. A demodulating system will later decipher this variation in frequency and translate it back into the original modulating signal. And due to the fact that frequency modulation cares about the frequency rather than the amplitude, random peaks caused by static are easily filtered and ignored, making frequency modulation much more protected against noise than amplitude modulation.
Welcome everyone, my name is Banda, and now we are diving into part 2 of our series on the evolution of radio. While part 1 covered the history and fundamental physics of radio waves, today we are focusing on the present and the future. We will be looking at the recent cutting-edge advancement in radio technology, and more importantly, exploring the why this century-old technology still matters today, and the profound impact it has on our daily lives. Let's start by looking at how the technology has evolved. When we think of radio, we often picture old analog dial and physical antennas. But today, radio is undergoing a massive digital transformation. It's no longer just about hardware, it's about software. To frame this shift, consider this insight from RF industry research. At its essence, on SDR represent a paradigm shift from traditional radio hardware to software-based solutions, enabling dynamic reconfiguration. What does this actually mean? It means radio has become a computer. This brings us to one of the most significant leaps in modern wireless technology, software-defined radio or SDR. Historically, if you want a radio to pick up a new frequency or use a new protocol, you had to physically rip out hardware component mixer, filters, modulator, and replace them. SDR changes all of that by replacing physical hardware with sophisticated software running on powerful processor. A single device can instantly switch between vastly different radio protocols just by loading new code. The benefits of this are massive. First, unmatched flexibility. A military unit or a commercial tower can reconfigure their system on the fly without touching a single wire. Second, it's highly cost effective. Instead of buying new hardware, you just push a remote firmware update, much like updating the app on your smartphone. And finally, it's enable cognitive radio. By integrating AI, this radio can actively scan the environment and automatically jump to the best, clearest frequency, optimizing bandwidth in real world. But advancements aren't just happening in commercial or military sectors, they are in your car right now. Digital HD radio is how modern broadcasters are pushing traditional FM and AM into the 21st century by transmitting a digital signal alongside the analog one. Station can multicast, offering up to three or four distinct channels on a single frequency. It provides crystal clear, static-free audio and allows the station to push real-time data directly to your dashboard like album art, traffic alert, and emergency weather updates. So the technology has advanced incredibly, but we have 5G. We have high-speed fiber internet. Why does radio still matter as a societal tool? Let's look at its real-world impact as a critical lifeline. We love our digital tech, but cellular tower broadband cables and fiber optics share a common weakness. They are incredibly fragile during severe weather, earthquake, or power grid failure. These networks overload or completely collapse. Radio, on the other hand, boasts unmatched resilience. It requires almost zero evacuation on the receiving end. One powerful generator-backed radio tower can reach millions of people who only need a simple battery-powered or hand-crank receiver to get the message. This isn't theoretical. Time and time again, radio proves to be our ultimate backup plan. During the devastating 12 2011 earthquake in Japan and the 2005 earthquake in Pakistan, mobile network and the internet went dark. In those terrifying days, emergency communication FM station became the absolute primary source of life-saving information. Authorities use it to coordinate rescue and tell people where to find clear water. When the grid goes down, radio restores order and provides hopes. Because of this reliability, our most critical global industries still run on advanced radio systems today. In aviation, air traffic control relies on secure, multi-band SDR to keep thousands of planes in the sky safe every hour. In the maritime industry, cargo ships use long-range digital radio to navigate oceans and send this distress signal for beyond the reach of any call tower. Any, and for emergency service, police and fire department utilize digital trunked radio system to maintain constant, instant coordination when second matter most. And finally, radio has profound hyper-local human impact. Today, there are over 5,000 independent community radio stations operating globally, particularly in rural areas or disaster-prone regions across South Asia, Africa, and Japan. These stations do more than just play music. They educate, they provide hyper-local agriculture and weather update, and they build community resilience in a way that the broader internet simply cannot.
Now we're gonna talk about misconception about radio waves. Now that we understand how AM and AFM communication work and how radio technology benefits society, let's discuss one of the most common misconceptions about radio waves. Many people use radio communication technologies every day without realizing it. FM radio, mobile networks, Wi-Fi, Bluetooth, and even satellite communication all rely on radio waves. However, despite how common these technologies are, there are still many misunderstandings about whether radio waves are dangerous to human health or it's safe. Radio waves and cell towers cause cancer. One popular myth is that radio waves from FM station, Wi-Fi routers, or cell towers can cause cancer. This belief usually comes from confusion between normal radio waves and harmful radiation, such as X-rays or nuclear radiation. Because the word because the word radiation sounds dangerous, many people assume that all types of radiation are harmful. But not all radiation is the same. We have two types of radiation. Radiation is divided into two main categories: not ionizing and radiation and ionizing radiation. Non-ionizing radiation includes radio waves, FM signals, Wi-Fi, Bluetooth, and microwave communication. These waves carry very low energy. They don't have enough power to damage cells or break DNA bonds in the human body. And we have ionizing radiation includes X-ray, gamma rays, and Saturn rays. These forms of radiation carry much higher energy and may become harmful with excessive exposure because they can damage human cells. FM and AM communication systems use non-ionizing radio waves, which are considered safe or for normal daily use. So, why are radio waves safe? Radio waves are considered safe because they are low energy electromagnetic waves. They cannot directly damage human DNA like ions radiation can. So, in conclusion, understanding the science behind radio waves helps us to avoid misinformation and better appreciate the communication technologies we use every day. AM and FM system continue to play an important role in the modern society by supporting broadcasting, transportation, emergency systems, and global communication. So, in conclusion, radio communication is not only safe when used properly, but it's also one of the technologies that keeps the world connected. Thank you.